a couple of collaborators we have from Cisco, Wojciech Tan and John Apostopoulos. They have been mostly so far engaged in understanding our problem formulations and providing feedback, and over time we will also hope to have some implementations. But this talk currently is more on the theory side. So I will give one slide just motivating the problem and why we are interested in. A general streaming setup is shown in the figure here. Typically, a source stream consists of a bunch of information packets. Each packet has a certain deadline with which it should be played back. If a packet is delayed, then it causes interruptions in the playback streams and various other artifacts as well. Now, different streaming applications have very different characteristics in terms of the required bit rate, the packet sizes, the delays, the packet loss rate, and so on. When we consider real-time applications, such as video conferencing and interactive gaming, the typical delays are quite small, typically 100 milliseconds and less. And so when we do coding for such applications, we have to explicitly account for the streaming nature of the source and deadlines, as we cannot have large buffers and so on. So the abstraction that I will discuss in this talk is the following. We have basically, at each time, a source packet coming in to the encoder. So at time I, the source packet Si comes in. We'll assume it consists of k symbols over some field fq. The encoder must operate in a causal fashion. So at time I, it generates a channel packet xi, which can depend on all the source packets up to and including time I, but not on the future ones. Okay, so it's a causal encoder. The channel packet will consist of n symbols, so the rate of the code is k by n. These channel packets are transmitted one at a time over a channel. We will focus on erasure channels. So either the output is an erasure or equal to the channel input, xi. So yi is either equal to xi or equals an erasure. Is
the memory finite in the encoding, or does it?
We allow right now for it to be arbitrary, but our constructions will typically use finite memory codes, as we will see. But the converses will be proven in this generality. The receiver must reconstruct the source packets again in a sequential fashion with a fixed delay. So here t is the decoding delay. So S0 must be reconstructed at time t, S1 at time t plus 1, and so on, one after the other. So we have this setup with a causal encoder and a delay constraint decoder, and this will be referred to as a streaming code in our talk. Now, the type of channels we are interested in should, it is often observed in practice that packet losses are correlated. When you have a packet loss, there will be again packet losses that occur in bunch. And these are typically modeled using models such as the Gilbert-Elliott channel. This is a two-state channel, where if the channel is in the bad state, packets are lost essentially with probability 1. So we see a bunch of packet losses here in bursts corresponding to the bad state. When the channel is in good state, typically it behaves like an IID channel with some small loss probability. So we'll see a few isolated losses as shown here. And so ideally, we would like to find the best possible streaming code for a given rate that minimizes the packet loss rate. This turns out to be a rather difficult problem. In fact, I think even computing the loss rate for a given code is quite challenging, because of all the effects from previous losses will carry over when the delays are finite. So because of that, we will focus on a simplification and consider what we will call a sliding window channel model. In this model, basically, we try to put local constraints on the type of erasure patterns. So it is defined as follows. If you take any window of length w, the channel can introduce one of the following patterns. Either you see a burst of length b, or up to n erasures in isolated positions. So take any local window of w consecutive symbols. In that particular window, you are allowed to either have a burst of length b, or up to n erasures in arbitrary positions. And the idea is we want to work with channels that have both burst and isolated losses, but it's somehow tractable so we can prove some results. Later on, we will see that if we choose the parameters in the right way, then codes for this particular channel will also continue to perform well over statistical models. So we'll revisit this in the simulations later on. So here is a recap of our system. We have basically a causal encoder. The erasure channel will be the sliding window channel that we saw on the previous slide. The decoder is a delay constraint decoder, where t is the decoding delay. And the rate of the code is k by n. we say a rate R is achievable over such a channel if there exists a sequence of encoding and decoding functions so such that each source packet can be reconstructed with a delay of t and over a field size that can be sufficiently large. Okay? So we do not put constraints on the field size, and the supremum of all rates will be the capacity. So this is the quantity we'll be interested in, the streaming capacity. I should note that this is a worst case definition. We are not putting any probability distribution over the channels in the sliding window model. Our code should work for all possible channels in this particular class. So no matter which channel comes up, the decoder should reconstruct each source packet with a delay of t. We are allowing for field sizes to be arbitrarily large. We are not trying to put constraints on that, although the coding schemes that we develop will be explicit, and we can bound the field sizes required in the codes. Okay. So I can now, unless there are any questions, I will move on to the results.
Do you need to let the field size get large to do the proofs?
Well, we need it to be sufficiently large because we are using some sort of constituent codes, like strongly MDS codes, that require a certain amount of field size. So I don't want to make it binary or make it, but I can give bounds on the size of the field size. The best codes we actually have field size which is like t cube. We have various constructions and field size. So the main result which appeared in this paper, which should just appear soon in IT transactions, is upper and lower bounds on the streaming capacity, which are essentially within 1 unit of the decoding delay. So our upper bound says that any feasible streaming code over such a channel should satisfy the following upper bound. R over 1 minus R times P plus N should be less than the minimum of W and T plus 1. And the lower bound says that there exists a particular class of codes that can achieve a rate R that satisfies the following lower bound. This is very similar to the upper bound, except that we have minus 1 on the right-hand side. So we are within 1 unit of the optimum delay in this case. So a couple of other remarks. If I fix the rate of the code, if I fix R, then this says that we cannot have very large B and N simultaneously. If I have a code that corrects long bursts, it cannot correct many isolated erasures and vice versa. They are governed by this particular trade-off. And later on, we will see that the properties required for burst erasure correction and correction of arbitrary erasures are different. One comes from span, the other comes from distance, and there is an inherent trade-off between these quantities. So that is manifested in this bound. Also, the right-hand side is the minimum of W and T plus 1.
Can you remind us what NBW, can you remind us the letters? I forgot.
So N is basically the number of isolated erasures. If you take a window of length W, in this window, you can either have a burst of length B, or you can have up to N erasures in arbitrary positions. Like I can do an example.
No, it's clear.
Okay. So it says that if you can correct a burst of length B, then that's the maximum value is this quantity. Or you can correct up to N erasures in that window. If you can correct a long burst, you won't be able to correct too many isolated erasures based on this trade-off. And converse, if you correct many isolated erasures, you cannot correct long bursts. And later on, I will explain why this trade-off comes from a structural point of view, like why certain structure is required for burst error correction and isolated erasures.
When B is 0,
right?
then N is greater than...
Right, so B has to be at least greater than or equal to N, because a burst erasure is a particular kind of erasure pattern. N is arbitrary, right?
Okay.
Those patterns are equally likely, or how do you...
We allow for it's a worst case definition. So take any window of length W, you can have up to N erasures or a burst of length B in the setup.
Is the burst included in the length, or
Is the
B included in N?
a burst erasure is a particular kind of an erasure pattern. You can have a longer burst, but up to N erasures. Maybe I should just do an example. I put it as a back of.
W, right? The burst has got to be less than W.
Yeah, burst has, otherwise the capacity is 0. That's in the theorem. So let me just do a quick. So here is an example of N equals 2, B equals 3, and W equals 6. So you can, if you take any window of length W, you can have 2 isolated erasures or a burst of length 3, and so on. If I take any consecutive window of length 6, I can either see a burst of length 6 or 3, or 2 erasures in arbitrary positions in this example. And any erasure pattern that satisfies this constraint would be in the class of my sliding window erasure channel. And so W has to be greater than B plus 1, which is given here. Otherwise, the capacity will be 0. So what I will do is mostly focus on how this lower bound was achieved and why the obvious construction does not work. Okay? So we'll start with a simple code construction, which is basically a systematic code. At each time, the channel packet xi will consist of the incoming source packet and n minus k parity check symbols. Okay, so let's say we have a structure like this. Each parity check is obtained by taking some linear combinations of the past m source symbols in this particular code. And basically, the way we generally think about parity checks is it will give us some sort of an equation involving the source symbols. So if I have like 4 packets that are erased, S0, S1, S2, S3, then I will basically wait until I have enough number of parity checks so that I can essentially invert the system of equations and recover the missing source packets. So here, if it's a rate half code, and if I have 4 missing source packets, I have to wait till time 7 until I recover all the source packets, and all of them will be recovered simultaneously. So in a sense, we want the system of equations to be full rank, and once it is, then we can recover everything that is missing. Okay? So in this particular, so if the coefficients of these H matrices, which have these dimensions, are selected at random, we get random linear codes where such full rank property is satisfied with high probability. There are also deterministic constructions, such as strongly MDS codes, which are convolutional counterparts of MDS codes, block MDS codes, that guarantee this full rank condition in a certain window of interest. But the main point here is that such code, when we think of parities as providing equations involving source symbols, everything has to be recovered simultaneously. And what we want are constructions where the source packets must be recovered sequentially. S0 should be recovered before S1, before S2. So somehow the construction should discriminate the source packets based on their deadlines. So I will explain to you how such a construction can be done in a simple example, and then I will sketch the general construction. And the example we have is that of a burst erasure channel. So imagine the channel only introduces an erasure burst, say of length 4, and say the decoding delay is 8. In this case, the optimum rate can be shown to be 2/3, and I will explain how we can construct a code with this rate. So what we will do is we will combine 2 simple codes, one of which is the kind of an erasure code we saw on the previous slide, and the other is a repetition code in a certain way such that we will achieve a code of the optimum rate. So the code on the top is a rate half erasure code. So if we have a burst of length 4, then we will have to wait till we get the 4 parity checks by time 7, and we will be able to recover all the 4 source packets. The code below is just a repetition code. A copy of each source packet is simply repeated with a delay of t. So t is 8 in this case. So u0 is appended to u8, the incoming source packet at time 8, and together they are sent at time 8. This is also a rate half code, but we are not doing any combination across the source packets, just a simple repetition. Okay? So let's put these 2 codes on top of one another. So what we have done is we have taken each source packet, we split it into u and v sub packets of the same size. We apply the erasure code to the v stream of rate half, and then we apply the repetition code to the u stream. So overall code also has a rate of half because we are just concatenating 2 rate half codes. And again, here the decoding will be done separately. The v stream will be decoded using the p symbols and the u stream with the last layer. So there's nothing done so far, but the key point is that the parameters were selected such that you can combine the 2 layers of parity checks, the p and the u symbols. In the last 2 layers, it turns out that they are not interfering with one another in the recovery process. So for this particular construction, we have 2 source packets and 1 parity check. This has a rate of 2/3. And if you have a burst of length 4, then from time 4 to 7, we can reconstruct all the v packets because the u's that combine with them are before time 0, so they are not erased. They can be subtracted out. So the p symbols are sufficient to recover the v's at time 7. Once we have recovered the v symbols, we can cancel the p's from time 8 onwards. They can be just computed and cancelled. So all the u symbols can be recovered sequentially from time 8, 9. The source packet is basically u comma v. So at time 8, we have recovered as 0, which consists of u0 and v0. At time 9, we have s1, which consists of u1 and v1, and so on in a sequential fashion. And this turns out to basically give the optimum rate. This particular idea can be generalized actually to any arbitrary burst length and delay. But the basic steps are sketched here. But the high-level idea is you should take a source packet, split it into 2 sub-packets of the right dimensions, which are shown here, apply a repetition code to one group, a standard erasure code to the other group, combine the resulting parity checks, and append it to the incoming source packets. And if the parameters are selected in the right way, we will get a rate of t over t plus b.
What did you say that they don't interfere? The equations, the coefficients are disjoint. Is that what happened? I missed.
So what happens is when you have a burst of length 4 here, u0 and v0 are both lost, right? u0 is protected via this repetition code here. And so if this was lost, and if p8 cannot be computed, this parity check cannot be used. Right. But it so happens that when we have a burst of length 4, we will be using p4 to p7 to reconstruct the v symbols. And at that time, we can subtract out the u parts, which happens before the burst. This is what I meant by the fact that the 2 layers.
The interference can be cancelled, I guess. It's not that they do interfere, but you always have enough to cancel.
Right. You have designed the parameters so that they can be cancelled out. Right. In particular, p8, which could be a function of v0 to v3, can be computed and cancelled out. So, to extend this beyond burst erasure channels, it turns out that the extension turned out to be surprisingly simple. When we have to correct both burst erasures and isolated losses, what we realized is that the main bottleneck when we have isolated losses is the repetition code. u0 is repeated again at time 8, u1 at time 9. So if I have erasure at time 0 and 8, for example, u0 cannot be recovered. So the bottleneck when we have isolated erasures in the sliding window model turns out to be the repetition code. And what turned out to be the right thing to do, at least as far as the lower bound was concerned, was to apply an extra erasure code to the u symbols, which is this last layer of packets, which are obtained by applying an erasure code to the u symbols as shown here and appending it to the previous burst erasure code. So we start with the burst erasure code, and then when we have to correct isolated erasures as well, depending on the value of n, we have an extra layer of parity checks as shown here. And by suitably selecting the value of k, we will be able to, in fact, achieve the lower bound that was stated in the theorem. So it has a nice architecture in the sense that we start with a burst erasure code, and then as we start seeing more and more isolated erasure, we can vary the size of the last layer to correct for these erasures. So now let me slightly change the direction and talk about some structural properties of these codes. What is so different in streaming than the original constructions? So I gave a specific code construction and achieves the lower bound, but let me talk about the problem slightly more abstractly. These are all convolutional codes, as was pointed out yesterday in my short presentation. Every time we take k symbols as input and generate n symbols as output. So typically, convolutional codes are most naturally thought of in terms of trellis diagrams. So the blue circles here are the states of the trellis, and the paths through the trellis represent the different code words. Classically, we try to design convolutional codes for maximum free distance. But when we have such delay constraints, it turns out that we should look at more local distance metrics. So here is a definition of the column distance of a convolutional code, which is actually known in the literature. Professor Costello has done a lot of work on this in the context of sequential decoding, but it turns out to be also relevant in the context of streaming problem. So the column distance is defined in the following way. We basically take the interval from time 0 to t. So this is the resulting generator matrix of the convolutional code in this interval, which is basically the truncated generator matrix. It has the block Toeplitz structure. And we look at all possible code words that are induced by all input sequences where S0 is non-zero. And then we find the code word with minimum Hamming weight in this set. So what this is really doing is basically, if you go back to the trellis diagram, it is looking for all code words that diverge from the all zero state at time 0, then looking at the code words in the interval 0 to t, and finding the particular code word with minimum weight. That is the column distance of the code. So the key is you have to allow for the first symbol to be non-zero for this definition to work. Another metric we need is the column span. The column span of a code is defined in a very similar way as the column distance, except you look at the span length. So the interval from the first non-zero symbol to the last non-zero symbol, and find the code with the smallest span. So that is the column span. And these properties can be shown to be directly related to the error correction over the sliding window model. We can show that a code is feasible over such a channel if and only if the column distance is greater than n plus 1 and the column span is greater than or equal to b plus 1. So our main result can be translated into a trade-off between the achievable column distance and column span. We can show that for any convolutional code, the column distance and column span must satisfy this particular upper bound. We cannot have a code with large column distance and column span simultaneously, and conversely, our proposed construction achieves this particular lower bound. And so in a sense, what we are doing is finding codes that simultaneously have good column distance and column span. And so we gave a name to these codes. We call them MIDAS codes, for maximum distance and span codes, it seemed to make sense in this framework. But we are not aware of such a result from the classical convolutional coding literature. So it might be interesting to see whether there are alternative proofs that do not appeal to our operational definition of the streaming setup. So let me now briefly go back and talk about statistical models and show some simulation results and then wrap up. So we will go back to the Gilbert-Elliott channel, which has two states. When the channel is in the bad state, it introduces burst losses. Typically, the burst losses will have an exponential distribution for the Gilbert-Elliott channel, depending on the value of beta here, which is taken to be 0.5. That determines the mean burst length. Alpha determines the gap between successive bursts. It's the probability for going from good state to bad state. We fix the delay to be 12 and the rate of the code to be about half. And when the channel is in the good state, we let the probability of loss be epsilon. So in the good state, the loss is not zero. In the Gilbert model, it is zero, but in the Gilbert-Elliott, we allow for some loss probability. And here is a simulation result we have. We vary epsilon on the x-axis, the loss probability in the good state, from 10 to the minus 3 to 10 to the minus 2. On the y-axis, we plot the residual loss for different codes. The blue line here is just the uncoded loss rate. As we increase epsilon, the loss probability will increase, and that is basically shown here without any coding. And there are three plots here corresponding to three different codes of the same rate when the delay is 12. The kind of horizontal line here, the black line, corresponds to a classical erasure code that achieves n equals b equals 6. So this code can correct up to 6 isolated erasures or a burst of length 6 in this window of length t. And so this code is very insensitive as we increase epsilon. As we start adding random losses, because of the large value of n, it can basically clean up everything. But because b is small, it basically suffers from longer bursts, and that is seen in this part of the code. The red line here corresponds to a code that can only correct burst erasures. So this corresponds to n equals 1 and b equals 11. And so as we start increasing epsilon, the performance starts to deteriorate rather quickly. Although when epsilon is very small, when we essentially only have burst losses, the code performs well. And our particular code that uses n equals 2 and b equals 9 in the family we have achieves a relatively long bursts and also can be robust up to 2 erasures and has the best performance in this regime. If we go to more sophisticated, higher order models, such as the Fritzman channel, then it turns out that the burst losses are hypergeometric distributions. In this case, we can actually get a lot better performance gains than the classical codes. In the Gilbert-Elliott channel, because of the exponential distribution, it actually somewhat favors classical codes. But if you have longer bursts, then we can get up to an order of magnitude gain over the baseline schemes, which is what is shown in this simulation. I only have a couple of minutes, so I will just quickly go and wrap up. We have several other extensions. So we have a multicast extension. The idea is when the channel is good, we should decode with a smaller delay. When the channel is bad, we should decode with a longer delay. And the problem from a coding theory point of view corresponds to finding codes with good column span profile. Not just looking at one value of column span for a given delay, but as you increase delay, look at the whole profile. And this turns out to be rather intricate, and we have some results in this particular paper. We have also looked at several other extensions, such as mismatch streaming codes. When the source arrival and the channel transmission rates are not the same, we have one source packet every M channel uses, then how can the construction be generalized? We have partial recovery codes that do not recover all the source packets in the stream, but a subset of them, and they are useful in certain cases, which was in this paper. We have dealt with multiple erasure bursts, multiple links, and multiple source streams with different decoding delays. So I will give, there's a couple of related works to this problem. There hasn't been a lot of work, but the problem of streaming over burst erasure channels was originally looked at Martinian and Sundberg. And actually, I should give a lot of credit to this paper, where they originally formulated the problem. Unfortunately, the construction was somewhat combinatorial in nature, and it was not obvious how to generalize it to these various other extensions. The layered coding approach that I presented here actually has a nice benefit that it could be generalized in many of the setups that I discussed. There is also related work, more recent related work by Leong and Ho, Leong, Qureshi, and Ho, where the authors have looked at similar streaming problems, but the connections are closer to network coding rather than the kind of burst and isolated erasures that we have been considering. So that pretty much concludes my talk. I discussed the problem of real-time communications over channels with bursts and isolated erasures. We introduced a new class of code called MIDAS codes that are based on a layered coding approach and achieves an optimal trade-off between column distance and column span, or a near optimal trade-off, I should say. In terms of future work, there are still certain channels that are quite challenging, especially when the burst gaps are small, and we are working on finding improved codes for these. I should mention we have also looked at the network streaming problem, where we have found rank distance counterparts of these codes. Instead of MDS convolutional codes, we are looking at codes with rank distance in the convolutional setup. It will be interesting to look at systems theoretic approach. So looking at dual codes for MIDAS, for example, understanding these trade-offs more from a fundamental systems theory point of view, and also looking at the probabilistic channels directly instead of doing the deterministic approximation and finding codes. Maybe there are good lower bounds on the loss probability directly for the Gilbert-Elliott channel, and that can be used to compare our achievability results. So I think I'll stop here.
Okay, any questions?
So, you had the channel could be one of two states. So, is that related to why you have two layers? So, if you allow states in your channel, would you be then leading to add a third layer?
So my intuition is that the reason why we need two layers is not so much to do with the channel. It is like, we had the repetition code and the erasure code. The erasure code deals more with coding across packets, right? And so we have to do simultaneous recovery. The repetition code is like intra-packet coding. You just take the packet and you repeat it. So it has a nice sequential part to it, but it does not allow coding across packets, so it is not robust. And so when we combine the two, we are balancing the trade-off between inter-packet coding and intra-packet coding. And that is why we needed to split it into two sub-packets and then find the right trade-off of how much in each layer to allocate. Right? We have designed codes with, like, say, burst and isolated losses and many other variants. And often it turns out we have to divide it into two groups like this and then find the right number of layers to add, like in terms of parity checks, to deal with different erasure patterns. So, but in terms of source splitting, we haven't really found examples where you go beyond two layers. But that's a great question.
I just wonder, I know the setup is a little different, but there were a lot of old bounds on combined burst and random error correction. Were any of those similar to the kind of bounds you got here? I mean, you could correct bursts of size B and a certain number of random errors within some, or with some guard space or something like that. Is
Right.
typically the way they were defined. And you're looking over a window, so it's a little different setup. But it seems like some of the parameters are the same, and maybe some of the bounds might be similar.
Yeah, it's possible. To be honest, I'm not too familiar with all the literature.
You gotta go back to the 1960s to find that.
But you are exactly right that if there is a sort of a window, like if the burst happens repeatedly, it in a sense defines the decoding delay. You cannot go beyond that. And then,
And so I don't think those bounds would apply directly because they didn't have a delay constraint like you've got. But there might be some.
so I think even looking at errors is interesting. I was only focusing on erasures, and I do believe there is a counterpart to errors.
Okay, let's thank all the speakers on the session.